Hello, my name is Reza Rokui. I am Director of Product Line Manager at Nokia. Today's talk is about intent-based 5G transverse slicing lifecycle management using a SDN controller product from Nokia. To this end, we start with some terminology. The term that we use during this presentation and in specific network slicing and transverse slicing. What are those exactly? After that, we go through the automation and assurance for the end-to-end network slicing, the process that needs to be done. We go through the role of the network services platform, which is the SDN controller from Nokia as a transverse slice controller for lifecycle management. And last but not least, we finish the thought with the QoS and network slicing, the differences and similarity between them. The important concept that we will talk about today, network slicing, we talk about the 5G, but it's very important to understand that as a technology, network slicing has various use cases. You can use network slicing for the interconnection of data centers, for example, or the operator can use that for the network sharing. But in today's talk, we will talk about 5G in specific, but it's important to understand, and in specific in the area of the transport, whatever concept we present here is really applicable to all the use cases, not only the 5G, but we will put all the examples in the context of 5G. Let's start with a network. I'm operator X. I have a network contains radio access network, transport, and core. I have a group of customers or tenant. In this case, I have BMW, Fiat, and public safety as my customers. Each of these customers are asking for multiple logically isolated network from left of this picture to the right. Left is my user equipment, UE, and the right side here is the application server which services those UEs. In this example, for example, BMW has 3 network slices, whereas the public safety has 1. The color here represents the SLA that each of these end-to-end network slice need. For example, for the dark gray network slice 5, most likely the SLA for the public safety service, video surveillance CCTV network slice is the bandwidth. Whereas for the autonomous driving, for example, for BMW, the SLA will be the jitter and packet loss. From the operator perspective, when it wants to create each of these end-to-end network slices, they have to create first the RAN slice, meaning in the context of each of these end-to-end network slices, they have to create a personality, a characteristic in the RAN equipment. Depends on your RAN equipment. That network function could be E node B, G node B, DU, or CU, for example. But the idea here is the creation of the personality, and in a practical way, meaning air interface configuration, group of policy profile configuration, QoS mapping, some level of the IP address allocation, VLAN, and so on. All this means the RAN slice will be created. Again, this is in the context of each end-to-end network slice. Similarly, operator should create core slice, meaning creation of the context and personality on the core equipment, UPF, AMF, SMF, and so on. And last but not least, they have to create connectivity between, in this case, RAN slice and the core slice, or between core slice and application. We call that connection transverse slice. Transverse slice basically means connection-oriented, which is specific for one SLA. To create those, again, from operator perspective, they need to have various controllers for RAN, transport, core slices, as you've seen here. And last but not least, they have to have an orchestrator, which look at the end-to-end context. There are 2 characteristics here. One is SLA matters. Each of these end-to-end network slices that we create is specific to one SLA. And the manual operation really doesn't work. In this context, the automation is very essential part of the end-to-end network slice. And basically, the automation is the theme of the presentation today. You will see we will talk about automation in a very general concept and in a specific in transport. Why we need that one, we will go through it. But this is very important aspect that manual operation is not really enough. We need to do the automation. We talk about transverse lights a few times. So let's go through some examples. In this presentation, I will give the context for the network slice 5, the dark gray few times. I refer to that. So this is the first example of that. Let's say from the operator perspective, their RAN is distributed RAN. They have G node B, which is equivalent of E node B. It contains all the radio access technology and BBU, baseband unit, everything is inside one box. I gray out the RAN and core slice because we are really not talking about it in this presentation. But from the transport perspective, we are creating connectivity between G node B's, for example, AMF and UPF, connection red and connection green through interface end-to-end entry. You can think of red as a control plane, for example, or portion of the control plane, and the green as the data plane. So we created two transverse slices, two group of connectivity, connection red and connection green, with a specific SLA. Also, we are creating connection gray, which in this case is a slice B. We are creating connectivity between UPF and the data center for this application server if they are not residing in the same data center. If it is, we really don't need transverse slice B. If we extend that concept for the same end-to-end network slice, you see the top end-to-end network slice for public safety, for the service type CCTV, there is really no change. The only difference is centralized RAN, meaning we take the G node B, we disaggregate it into the BBU portion and the RU portion, radio portion. And we will put a network, so-called low latency front haul, which is very sensitive to the latency in the middle. So from the perspective of transverse slice, the transverse slice A and B stays exactly the same as you see in the picture. The only difference here is we have to create another set of connectivity across radio and BBU through the front haul network. And we call that one transverse slice C. We use SLA blue in this case. If we extend the same concept one more step further, we come up with the Cloud RAN. In the Cloud RAN, we basically take the BBU, disaggregate it to the real-time and non-real-time component. We call it DU and CU respectively, and we will introduce another network called high latency mid-haul in the middle. The high or low in this case are relative. It means that the latency is higher than the front haul. But again, for the same end-to-end network slice as you see here, the transverse slice A, B, C stays the same. The only difference here is we have to create another set of connectivity through the mid-haul network for F1 connection, F1 interfaces between DU and CU, and we are introducing transverse slice D. So the idea here is, as we change the deployment, the number of transverse slices might change, as you clearly seen in this example. Another aspect here is the transverse slice by itself is a technology agnostic. We didn't talk about how to realize or implement each of these transverse slices A, B, C, D in the network. We will talk about that, but the portion that we are referring here is a transverse slice definition. Realization is a technology specific, and we will talk about that in an IP and PLS network, for example. Now, we have a good concept about end-to-end network slice and transverse slice. Let's go through the one generic network, the flow that should happen in the network in a very high level from the customer portal all the way to the network. Let's assume I want to create the network slice that we discussed before, dark gray network slice 5, and this is my network. I want to create this one in my backhaul network between RAN and core. From the perspective of the operator, orchestrator receives a request from the customer that I want you to create me an end-to-end network slice 5 in this example. Orchestrator goes through the process, and the first thing that it does, it goes through the step 3A all the way to E, which basically means it talks to the RAN slice controller. RAN slice controller create that context and connect in the RAN. It uses the mediation. RAN and FMF, the network function management function, is basically the mediation layer. The RAN slice will be created. Similarly, if we go through the step 4, the core slice will be created. You will see there are conceptually the mirror image of each other. And last but not least, orchestrator sends a request 5 to transfer slice controller to realize the transfer slice that we need in the network. For example, in this case, transfer slice screen. Interfaces 3A and 4A are defined by 3GPP, whereas the interfaces 5A currently is defined by the IETF, and Nokia has the proactive role on defining that interface. I put a draft that currently addressing that. The characteristic of transfer slice controller, the framework, there are a group of drafts. If you go to IETF and search for the network slice IETF, you will see a group of the relative information about that interface, about the characteristic of the transfer slice controller, and so on. Another aspect which is important, the same process that is shown here for the backhaul is applicable to the front haul and mid haul. So for example, transfer slice blue and red, same process will happen, but the only difference here is, in this case, the network functions are, for example, DU or CU from the mid-haul perspective, or from the radio head to DU for the front end. But conceptually, the concept of the transfer slice, the connection, is exactly the same. Now, let's go one step deeper to see what is the role of the SDN controller from Nokia to basically realize everything that we discussed today. So far, whatever we discussed was very general concept, and it was basically 3GPP IETF perspective from the network slicing and specific transfer slicing. Now we go one step further about the product that we have and how it basically works in the context of the slicing. Nokia has a solution for SDN called NSP, Network Services Platform. This product provides you with the 3 major functions: service automation, optimization, and assurance. These 3 major functions are abstracted from the northbound RESTful API, Yang-defined model, and very specific from the southbound. We are multi-vendor, multi-technology, and multi-layer. And whatever has been done, basically we leverage all these 3 functions in the context of the 5G transfer slicing, meaning we do the automation of the transfer slicing, creation, deletion, modification. We do the closed loop optimization of transfer slices, and last but not least, we do the monitoring, analytics, and assurance on those transfer slices. If we look at the NSP and the transfer slice controller, this is basically the same idea from the different viewpoint. Today, NSP has a group of capabilities, functions. The boxes that you see here, the black boxes that you see here, they are not modules, or they are not VM, but rather functions. We, for example, provide the path computation element or optimization functionality. We provide service provisioning. We provide multi-vendor capability, analytics, and so on. The same NSP is extended to have another capability, TSC, Transport Slice Controller, is a new capability on NSP, which basically provides you with the full lifecycle management transfer slices in the 3 areas. Those 3 areas are automation, monitoring and analytics, and closed loop optimization. And basically, the message of this slide here is, if you are a customer and using NSP today, introducing TSC is basically to fully preserve the investment that you've done so far on NSP. The same platform can be extended, can be used for the transfer slicing, and this is basically means that your operation team, for example, can use the same idea that they have so far. They have used NSP, and from that aspect, basically, we are preserving whatever you have already done with NSP, extending it to the transfer slice. So in a summary, NSP as a transfer slice controller gives you 2 contexts. Transfer the slice front end, which is a single pane of glass is a transfer slice centric. When you go here, you don't see service, you don't see LSP, you see transfer slice that, for example, I created for the BMW or for the public safety. And it gives you all the information, everything that you really need to know, all the services, LSP, tunnels, assurance aspect. But from the back-end logic, we introduce a intent-based programmable logic to realize a transfer slice, meaning depends on what you want to use, which technology you want to use. We basically giving you a hot pluggable way of realizing transfer slice, and also we giving you the assurance concept. So basically lifecycle management is the automation part, enablement part, and the assurance. And these are the two cornerstones of any transfer slice: enablement, assurance, which basically means monitoring, and closed loop optimization. This is a very typical way of realizing a transfer slice. This is not the way to do it, but this is one way of doing it. As you see here, the same transfer slice can basically manage transfer slice across frontal, middle, and backhaul, which means that I have a single pane of glass. Regardless of which technology is used in each of these domains, I can use my transfer slice controller for lifecycle management. And the important aspect from the Nokia is this context, the transfer slice control that we created inside NSP is based on the intent manager framework. This is a framework which is highly programmable, it's hot pluggable, and from that aspect, TSC is using the same technology and the same framework to realize the transfer slice hot pluggability and programmability. And this is basically a very important aspect that if you want to realize a transfer slice, let's say today with non-TE concept, and tomorrow you want to change it to the TE path or tunnels, the way that we design TSC, this hot pluggable, you write your business logic, you put it on the NSP, and basically from that on, the way that you want to realize the transfer slice will be there. If we put everything together here, from the operator perspective, you will see that I have a network of n number of RAN nodes and m number of the core nodes. There is a slice, a transfer, network slice yellow already created in some of these RAN. I put it here for the specific reason that we will see momentarily. When customer wants to create the end-to-end network slice for the same network slice 5 that we discussed before, the RAN slice will be created, but as you see here, RAN slice will be created on, let's say, 2 RAN nodes and not n number of nodes. So basically a subset of those nodes. And in this context, RAN node 2 has right now context for the 2 network slices. Similarly, their core slice will be created. So it will, out of m number of UPF, 1 UPF will be selected. And last but not least, the transfer slice, which is a connectivity between the green context on the RAN side and UPF, will be given at step 9 to transfer slice controller. And transfer slice controller goes and realizes that when using various services, tunnels. Step 9 is technology agnostic. Step 10 and 11 are technology specific. If I go one step further, extend step 9, 10, and 11 in the next slide, you will see here the same network. NSP receives creation of the transfer slice at the step 9. At step 10, we go using the infrastructure of the NSP to create the services that we need. And after that, we go through the PCE and path computation and we create the tunnel. The important aspect here is all step 10 and 11 are really abstracted from the operator. They don't see that one because we provide all the intelligence that we need. And basically from customer perspective, they see a step 9 and creation of the transfer slice. And under the hood, we do all this automation part, and this is basically the essential aspect of the TSC. We are also doing the monitoring analytics, as I mentioned. We collect the telemetry data from the network, and from that aspect, we basically providing all the statistics. We gather all the statistics, OEM related stuff from the network. We aggregate it in the context of a transfer slice, and we show that in the dashboard, for example, and we use that one to say whether or not a transfer slice is healthy or not. And also for the closed loop optimization, we use that telemetry data to close the loop. If something happened, let's say in the transport red, we have to do the reroute, we do that one under the hood. And this is the whole idea that basically the whole full lifecycle management will be addressed by NSP. The last section is about the similarity and differences between QoS and 5G network slicing. The concept of the network slicing and QoS are independent, are orthogonal. This picture is showing why this is the case. If I have, let's say, two network slices, slice 1 and 2, which is blue and yellow, each of these network slices are created for a specific SLA, as we went through the presentation today. However, each of these network slices can be used for various QoS flows. This is the lowest granularity that the 5G allows you to control the QoS. From that aspect, you see, for example, the blue network slice can use QoS number 8 and 6, and network slice yellow can use QoS 8 only. From that aspect, network slicing and QoS are independent. We can create a network slice, and we can use that one for various QoS flows. And basically, the idea of the network slicing and QoS in this case shows that they are how independent they are. If we put everything from the data path point of view, how we can enforce the end-to-end QoS, this is one possible solution that, for example, we can do. There are two UEs, two network slices, blue and yellow, as you see here, from UE all the way to the RAN, to the transport and the core. The concept of the QoS should be enforced at each step that we go through the traffic flow. The traffic from the UE comes to the RAN with the specific 5QI, which is basically the characteristic of the QoS that a specific data flow needs. It goes to the RAN. It will be translated to DSCP concept for the IP perspective. And when it arrives at the cell site router, we enforce the differential services. Basically, we map that one to a specific forwarding classes and queues. It becomes IP packet, goes through the network, and after that, it becomes MPLS packet. We have to enforce QoS at the MPLS with the experimental bit, and as the traffic goes through the network, basically, we have the same characteristic for the QoS. Same thing will happen for another flow. In this case, I have number 3, which goes through the yellow slices, and same thing will happen. So basically, the concept of QoS should be applicable or should be applied to any stage of the packet flow from UE all the way to the core. If we put everything together that we discussed, the first concept that we discussed was concept of the end-to-end network slice and in a specific transverse slice. What are those? What are the characteristics? What are the similarity differences? The second concept that we discussed was about transverse slice management, lifecycle management. We introduced NSP as a transverse slice controller. This is a capability on NSP, which provides you with the 3 major ideas that we have to address for transverse slice, meaning automation, monitoring, and closed-loop optimization. And last but not least, we discussed about characteristics of the NSP as a transverse slice controller. Why TSC from Nokia? We discussed there are 2 aspects, front end, back end. Front end is transverse slice centric, which addresses everything that we want to know about transverse slices created in the network. And the backend is the intent-based logic, which allows you to do the programmable functionality of the TSC. Thank you for your attention. And as usual, if there is any question, please talk to the customer team. Thanks. Bye.